Okay, good morning. Thank you for coming. Today, we're going to still carry on our example of combined thin and non-thin wall example. Then we're going to look at longitudinal shear on the beam section. This first hour or first 15 minutes, I'm going to do more examples. Okay, just a brain teaser. Okay, how will you design the shear flow for a section like this? Can you all try? Okay, how will you design a shear flow section like this? Okay, so I want you to like take 20 seconds. Okay, come to your mind. Okay, think about how to design the shear flow for this. Okay, so the shear stress, the shear force is coming down from the top. Okay, it's coming down from the top like this. Okay, so how will you design your shear flow? Okay. Okay, since you guys are all here, I need you all to be verbal with me. So how will you design it? Talk to me. Come on. Anyone? Yes. Okay, so down, out, right? Okay, anyone else? So what controls the shear flow direction? Anyone? Yep. Yep, the terminal, but the direction, what controls it? The top, right? The top controls it. Okay. So sorry, the web. Okay. Right? The web controls it, right? So everything has to flow downwards. Okay. Now you come up with a good answer. Okay, you come up with a good answer. Okay, so the answer that was given, come on, can I copy and paste? Okay, so there are two things you will have to see. Okay, so both. Okay, I'm going to draw the left and the right. So both come in this way. Right. So one of the answer is Q go this way. Am I right? Right? And then Q go this way. Okay. Now the question is, if we want to find the shear flow at point or shear stress within here, right? Let's say we want to find the shear stress exactly on this line that I draw in red. Okay. What area do you take? Yeah. You take this area down here. Okay. You take that area down there. Another way to design, okay, another way to design this, right, is you can design the fluid because the mainstream is coming down here, right? The fluid is coming down vertically. You can also design this way. Again, if we want to find this section, right? Again, you take this area. Okay? So now, question for you. If we want to look at stresses at point A, right? We want to look at stresses at point A, right? The area we have to consider for point A is this area. Agree? This is for point A. On the other side, it's also for point A. If we want to look for point B, right? So this is for point B, right? The green. So both design are the same point B. How about if you want to look at point C? You take the whole what? area. So if you want to look at point C, right, you have to take this whole section down here. You know what? I'm going to cut and paste another one. If you want to look at point C, this is the area that we have to. So I'll divide it this way. Okay, this is the first moment of area we are going to look at. Do you see why I'm emphasizing down here? I'm always emphasizing the first moment of what? Area. Yes or no? V is constant. I is Mickey Mouse to find. T is the thickness, is visual. It's the first moment of area that's always messing us around. Okay? Right, so this is a good brain teaser. Okay? I think it's a very interesting problem. Don't you think so? Yes or no? Right? But once you understand the concept, number one rule is what? Not number one. The most important rule is what? The web. Huh? The web controls the what? The flow. Okay. If you don't see that the web controls the flow, you just stand out there. Oh, this is going to be tough. It's not that bad. Okay. Okay. Let's go back to this problem. Okay. So just to quickly recap, this problem that we have is a combine of thin wall and what? And thick wall. Okay. The previous example, we have a combination of box beam and white flange. Yes or no? Right. So for this example, we are going to look at thin wall and non-thin wall. Okay, I should not call it thick wall. I just say non-thin wall. So now, where we stop on Wednesday, we found that the shear stress at point C. Okay, and just to quickly recap, if I'm going to draw a line, this is where our centroid is. Okay, this is our centroid is. And we realize that, just to quickly recap, where is the thin wall section? Anywhere above this region is called thin wall. Okay, and then within this region is non-thin wall. A student asked me on Wednesday after class, how do we know whether is it thin wall or non-thin wall? Okay, in the test, which is your term test 2, I will tell you when to use thick wall and when to use what? Thin wall. So don't worry. Okay, so as an engineer later on, when you go to industry, then you have to make that decision whether is it a thick wall or a thin wall. Okay, now, so now we found shear stress at point C, right? Then we want to find the shear stress at point B. Okay, so the shear stress at point B is still a white flange analysis. Now the Q changes. Sorry, the thickness changes. So if we were to design our shear flow, okay, if we were to design our shear flow will go this direction. Right? Remember, we designed the shear flow. Why I deliberately want to design the shear flow down here is because then you know what thickness to take. Okay, so the thickness is perpendicular to the what? Shear flow direction. So for this case, now the thickness is this direction now. Okay. Anyone, anything not clear, stop me now, you ask now. Okay. So from here, we realize it's white flange. You only have Q, and now we know that thickness is equal to 0.02 meters. Okay. So the first moment of area that we are going to consider for this structure over here is this entire section now. Okay, I hope you all can see where I'm trying to draw. Okay. Right, that is the entire section we will draw. So now Q about the z-axis, now it will be at point B. Now this will be equal to, so we have to add in the 22.5 times 10 to power of 3, right? So that is for the shaded section. Next is for the web section. So the web thickness is 20 millimeters. The depth is what? The depth is 50 millimeters. And then the Y bar, so from here to here is 25, right? And then we know from here to here is 60. Okay, because there's 160, not 60. Come on, Eugene, wake up, wake up. Okay, so from here to here we know is 25, because 40 plus 10 is 50 divided by 2 is 25. This is 160, so from here to here is what? 80. So it will be 80 minus by 25. So this will be equal to 22.80 minus 25 times 20 times 50 is equal to 55. So 22.5 plus by 55 times 10 to the power 3. So I get 77.5 times 10 to the power 3 millimeter cube, and this is equal to 77.5 times 10 to the power minus 6 meter cube. Okay. I need to check. I have not a clue whether it's correct or wrong. Yep, it's correct. Okay. Then from here, we can find our shear stress at point B. It's equal to Vy over Izz. Now, we don't know anything about Vy over Izz yet, okay? Right. And then the first moment of area is 77.5 times 10 to the power minus 6. We are aware that the thickness is 0.02. Okay. So this will be equal to B 77.5 power minus 6 divided by 0.02 is 3.875 times 10 to the power minus 3 Vy over Izz. Okay. 3.875. Okay. So now, what we see now is stress at point B, the coefficient over here, right? The coefficient over here for point B is higher than 2.24 at point C. Okay. So there is one more area that we need to check, is to check at point A, right? Yes. No, the means the it's not that okay. You are looking at it. You're not right. You're not wrong. You're right. You're looking at it as a different perspective. Okay. What it is when it's a box beam, right? At the terminal, the Q split, one towards the left and one towards the right. Okay, so that's why you divide by 2. You can look at it, okay, Eugene, I'm going to divide the area by 2. Okay, but I rather teach it terminal, because later on, when I have more complicated shear flow, you have to grasp on that concept. Okay, you're not wrong, you're correct. Okay, right. So the next one we are going to look at is to look at point A. Okay, now this is very similar to your term test question. Yes or no? In your term test question, what did I ask you? Find the maximum shearing stress and find the shearing stress at the what? Centroid, right? In your term test, could you remember that? And not necessary, the maximum is at the what? Centroid, right? Why is that? It's because of this. If we look at the equation, okay, if we look at the equation where you have shear stress is equal to V over I Q over T. We know that the fact that this is a what? A constant, right? The way I teach you is those two are constant. What is fighting is this. When Q is maximum, there is a possibility that your shear stress will be a what? A maximum. But with T being the minimum, right? It can also increase your what? Your shear stress. Agree? Right? So both of them are always like fighting one another. So at point A, which I'm going to copy and paste down here. Seriously, my bad. Hold on, do apologize. I just want to copy the picture, please. Yes. Right. Now we have